Now may we invite Professor Helen Mann to introduce our next speaker. Professor Mann, please. So good afternoon again. Welcome back from the break. I'm delighted to introduce my colleague, Professor Sid JAGGI. I've been working with Sid on based on some of his rich experiences in flipped classroom teaching. And so I'm actually very much looking forward to the formal presentation of everything that he has done. So brief biography of Sid. He obtained his bachelor's degree at IIT Bombay, India, his master's and PhD from Caltech, all in electrical engineering, and he was a postdoctoral scholar at MIT. He has been with the Department of Information Engineering since 2007, and he is an associate professor there, conducting mathematical research interests on information and coding theory. In addition, he has been conducting research on innovative teaching and learning methodologies in his flipped classrooms, and he has won several teaching awards at CUHK. So please join me in welcoming Chris. Sid.
Thank you for the kind introduction, Helen, and it's a privilege and an honor to be talking here, especially after Chris. Even though it makes my life harder, it's hard to follow Chris, right? I'm going to be shamelessly. So it's encouraging to see that I've been to several talks on flipped classrooms recently, and many of them end up following roughly similar structures. So actually, many of the techniques that we're using, shooting videos and all of that, but then some follow-up exercises at home, some exercises in class, collaborative learning, group-based discussions, forums, all of those. Those are things that we also follow with a similar pedagogical structure, and therefore, I won't spend quite as much time as Chris did on the details because he's done such an excellent job about talking about those things. I'll focus on a few specific things that we're doing a little bit differently over here and just dive into those a little bit more deeply. And I'll talk about that. Also, maybe some of you noticed this coin over here. So just to get it out of the way, it's basically, so the first time I started teaching, I was giving a lecture, right? One directional communication. And I would be like, okay, any questions? Does anyone want to ask a question? Nobody would ever ask a question. I once gave a 2-hour lecture with a coin like this. And I'd be like, any questions? And nobody gave, though they were all staring really intently at my face. And, like, is it going to fall? Is it not going to fall, right? But now that now I've tried the same exercise in a flipped setting, and they're much more comfortable asking me, well, firstly, what are you doing? Is this a strange Indian custom? And then from there on, it goes on to, well, okay, how do I solve this question, right? So that's the nice thing about flipping classes, as Chris mentioned. It's just more fun. We are humans, we deal with human beings, and using the fact that we are human instead of being robots. I mean, I know as an engineer, it's supposed to be very, directed, methodical, step by step, but we are human social beings, and using those social structures are important. Anyway, so let me dive into it. The first few slides are just an overview. So this is a joint collaboration between CUHK and MIT, and in particular, the world's changing, technology is changing, and education kind of has to change too. And in particular, not just the content, not just how to deal with changing technology, but also how it's delivered. And Chris gave examples of how this is the case as well, right? So the fact that you now have video on demand at home, that was not possible 20 years ago, now it is. The fact that we all have mobile devices at our disposal, the fact that we can write apps which will do things. So the mode of instructions can change, will keep changing. Like what we are doing right now is not the end all and of the best thing, like the best possible way to teach yet. So there's a lot to be done, I think, in education 2.0, 3.0, right? And it's exciting to be at the beginning of this change in technology. So of course there are traditional classrooms, and they've served us well. Like humanity has pulled itself up from the marshes by classrooms, by basically a single person trying to give information. The first wave, I would say, of like trying to use new technologies for large scale for education was MOOCs, where the idea is, well, we create the best possible lectures, right? Put them online, and then everyone will just use them, and then there's no point for us educators anymore, right? Everyone will just be sitting at home learning, and that'll be it. We won't need universities anymore, at least to provide undergraduate education. But that first wave of educational technology has not borne out well, in the sense that completion rates are abysmal, the actual learning outcomes are measurably worse. It's not necessarily a great way to do things. So as Chris mentioned in his wonderful talk, like blended learning technologies, flipped classrooms in particular being a particularly important version of those, are really useful. They really measurably help students considerably better than most other methods do. So these slides are due to one of the teaching assistants, Boris here. He's done some funky animations, thanks to him. So yeah, just to dig into that a little bit, as Chris mentioned, so there's, in a traditional setting, there'll be a single point of information dissemination, the instructor, and then that's the lectures, and then you do some homeworks by yourself sitting at home, whereas of course in a flipped setting, the structure is flipped. You sit at home and first just get the basic content delivered to you, and then you come together and in a social setting, do some classroom activities with your peers, but also with the instructor or TAs or things like that. A quick shout out to the other CUHK and MIT academics here. I'm not going to call them out by name, but just so that you know some of the people who have been involved in these things, and also Professor Victor Zur and Chris TERMAN, but also Professor Stephen Ward, who is not here. So in particular, I'm excited to be, well, the first of the CUHK speakers. I'll be followed by Professor Darwin Lau. And both of us are from engineering, but in general, this discussion that will continue over the next couple of days is quite cross-disciplinary. Like we're engineering teachers again, but there are faculty from the Department of Education who are involved and helping us understand the use of educational pedagogy, but also social sciences, and thinking about because social structures are quite important in figuring out how to incentivize people to discuss things with each other. So like it's really quite a nice synergy, I think, that's going on in this group discussion. Okay, so let me dive into, in the next 15-20 minutes that I have, into some of the details of what's going on. And I'll frame it in a slightly, it's actually quite similar to what Chris did, but I'll frame it just slightly differently in a slightly more granular level. So Chris thinks of it as see one, do one, teach one, and that's roughly analogous to this so-called Bloom taxonomy, which is quite well known in the educational literature. So think of it like a food pyramid for teaching and learning, right? So at the bottom layer, there's sort of the base things that the carbohydrates, the carbs, are sort of just getting facts to you, right? So you look at a textbook, you listen to a lecture, or something like that, and you remember it. Okay, this is the formula to use in this context. At the next layer, it could be things like understanding. Okay, so given this formula in this context, how do I apply it? Like, how do I measure my basal metabolic rate, maybe, or if I lose this much weight, what will my BMR change to? You know, basic tweaks like that. And then as you go up, you keep doing more and more sophisticated things. You maybe think about, well, are there other tweaks to the BMR that you could use which are better in certain contexts? Is it really the best thing? And so on. And really right at the top, you're actually creating new knowledge which was not present in humanity before, right? And ideally, in a good class, you'd like to push as many students as far up this taxonomy as much as possible. So the way I'd like to frame the activities I'll be talking about will be really like just give you examples of the various things that we do in this class that go in those directions. Just to give you context, like Chris did for his class, so the context for this particular class that I'll be using as a case study is this class we call ESTR 1004, which is it's an engineering course. It's a freshman engineering course, first year engineering course. So it's basically second semester. They're 6 months out of high school. It's a class on linear algebra and vector calculus. So for those of you who know these things, it's basically how to multiply matrices, how to use some linear operations and things like that, how to do basic derivatives, things like that. So that's the traditional class. But this stream, this cohort of students, 42 students, is our so-called elite students. These are the smartest of our students, of our engineering students. It's a self-selected group. So they really are quite smart, but nonetheless, I've seen them do amazing things at the level of basically almost first-year graduate student. So I'm really quite proud of them. And we arrange them into groups of, so almost all the activities in class are group-based, so groups of 3 each and so on. So okay, at the basic level, there are video lectures. So I created videos, not nearly as nice as the ones that Chris has, nowhere near the number of views, but the idea is just quick and dirty. So 100+ videos between 5 and 15 minutes each. So you shoot these videos, put them up online, YouTube, students can go watch them and so on. And along with this, just like Chris did, so interspersed between each video, there'll be some basic exercises, and these exercises are from what I saw in Chris's talk are quite similar to what Chris does. Okay, so here are 2 matrices, multiply them, and this is what the answer should be, and it automatically checks. And if you don't get the answer, there are hints and there are explanations and so on. So these are automated response systems. So at least they get a baseline level of understanding of, okay, this is how I do the mechanical procedures, the formulae work, and so on, right? These are relatively easy to set up, and if you get the wrong answer, it gives you those feedbacks. You can set up trees and so on. So it's quite good at giving at-home instruction. This looks like garbage, but I mean, if you understand a little bit of LaTeX, it's really like a couple of minutes to code up an exercise. So it doesn't take too much effort, and it's really worth the effort. So it's quite nice. All right. So then at the next level, this is when they start coming to class. So what would normally be a lecture, they come to class and they do in-class exercises in groups. So this is where the social aspect of things starts kicking in. So they've hopefully done the baseline exercise, the baseline video watching and exercise at home, and we can monitor this. We can monitor which fraction has watched videos, which individual students has watched videos and done exercises. And those who haven't, we can be like, hey, I noticed you haven't been watching videos. What's going on, right? There can be peer pressure. There can be like hard thresholds. There are various ways of incentivizing that desirable behavior. But once they come to class, that's when the real work starts, where we start pushing them up further up and giving them more complex tasks to try to figure out. So there are in-class exercises. So this is an example of a worksheet. It's too hard to see what's going on, but really what's like at those red things are sort of baseline questions. Here's how you multiply matrices and so on. Try to do some basic exercises. The green things are somewhat challenging questions. These are things that if a student answers them in a final exam, you'd be really quite happy because they really do understand like some non-trivial details of the mathematics going on. And then there's usually a few questions which are we call them Harold questions. Harold standing for hypothetical, alert, reader of limitless dedication. Someone who just spends all his time just finding out knowledge for the sheer pleasure of finding knowledge. So if someone's already done all the basic questions, then they can spend time on these things. So these are, as Chris said, and it's the same here. Like these worksheets basically contain all the concepts that are contained within the class. So in each week there'll be a worksheet which will be distributed, a whole bunch of questions, and then we'll break the questions up into different subsets. So for example, over here, different groups. By the way, they chose their own names. So there was the mythical creatures group, the flying creatures group, so they all chose very inventive group names for themselves. And then each group gets a different subset of questions to attempt. So they are primarily responsible for answering their own questions, but then each group gets to come in and present their solution, or different subsets are given the choice to come and present their solutions, and they listen to solutions from other groups and so on. So they also hopefully learn from each other. As part of this, okay, so first of all, they're sort of, in this class, they're sort of learning from each other. Note, it's a slightly different setup than Chris. We don't have these nice square tables. It's a computer lab repurposed for this. But it's similarly nice to walk around. So it's really quite useful to have space. It's not like this. This would be terrible to give a lecture in because, you can't really go and access the students, right? You need to be able to go talk to them. So it's a more free-flowing setup. Students are walking around, TAs are walking around. Once they get solutions, they come to the front, they present the solutions, which are projected on the screen, but then that same thing is also piped to each individual's computer on the thing, so they can see local versions and all of that. So it's quite nicely set up. I think the tech team here has been amazing, so that's been very nice. And here's, so as I mentioned, social engineering is key to all of this. So one thing that we're doing here that's been amazing has been, so each group is supposed to answer a few questions, right? So each student in each group is supposed to turn in their own version of the solution. It's fine if they talk to each other. Indeed, they're incentivized to talk to each other, learn from each other. But what we'll do is we'll randomly select one, and the whole group gets that grade for that question. So the purpose here is, if you know the answer, you'd better teach your peers, because that's the way to guarantee that you'll do well, right? So actually, quite 50% of the class grade is based on group-based activities. And you know, in all honesty, almost all of them end up getting these 50 points. But these points basically are useful to incentivize positive behavior. So I'm happy if everyone gets full points in these 50, like in half this class grade, because that engenders positive behavior. So that's what we use these points for. There's feedback after every class, so they each get a slip, like that slip at the top, which says, okay, what do you think of today's class, 0 to 10? But really the most useful thing is at the back, give us comments. And by the way, they also choose a secret ID at the beginning of each semester, so then we can track longitudinally the comments that students are giving over a period of time. So they give their comments, I try to give feedback, and then we summarize it, and they can see it. So this is a way to, you know, immediately address, like after each class, okay, these are the pressure points. This is, okay, I didn't understand your handwriting. This concept was hard to understand. I wish you'd spend more time on this. Or can we discuss this more in some other class, things like that. So it really ends up being quite useful as a way of quickly controlling you know, issues and getting back to them. So, and improving. One other thing that we innovated on and that I'm quite proud of, excuse me, is this thing that we call the MATE system, so the Market Assisted Teaching Exchange system. So what is this? What this is okay, so you've gotten to a certain point, you've tried to exercise, you've tried to learn as much as you can, but there's still stuff you don't understand. It's really somewhat complicated. You really don't know what's going on. And you know, in an ideal world, I would have an infinite amount of time to spend with each student and discuss their problems, but I don't. There's one of me, there's 40, 50 of them. What do I do, right? So we set up a marketplace for them to exchange their ideas, right? What does that mean? So each week, they're given an opportunity at the end of the week. There's some classroom time devoted to the following activity. It's basically, before they come to classroom, they have to fill in the spreadsheet. And like the spreadsheet, each column corresponds to a distinct concept, like a video, a exercise, something, like something, some discrete object that they should understand. Each row corresponds to a specific student. And they're supposed to enter, so each student is responsible for a row, and that student is supposed to enter, I understood this topic, I did not understand that topic, right, at a granular level. So once they come into class, then they're given these, so they're given these coupons. So this is a fake Hong Kong dollar. So this coupon, they're each given a few of these, and they can, you know, they're like, oh, okay, I don't understand like topic X. Let me use that spreadsheet, which is now publicly viewable, to find someone who can help me with topic X, like someone who has a high score on topic X. It's self-reported, but you know. So then they go, they walk around, they're like, oh, okay, that person can help me. They walk around, and then if they're satisfied, they write down the topic number, the person who helped them, and so on, and then they exchange that. Now, this is great in the sense that so I'll come back to that slide, but so for example, in 1.5 hours, like over 50 plus distinct concepts were exchanged, 100 plus total interactions, more than 3/4 of the students were helped, like within a class of just 42 students, so that's really quite effective, right? Like if I was a single instructor trying to help the students, or even with the TAs, it would be a far smaller number that we'd be able to help in this given period of time. So as is often the case, markets are just a better way of allocating scarce resources. So this was really quite useful, and we really liked it. There are other advantages as well. But beyond this, it's also quite useful in a couple of other ways. It's predictive of future performance. Like if you see how the students are interacting, because what's the other advantage of all of this? We can do data analytics, right? This is the Stanley Ho big data analytics, something or the other. So we're getting a whole bunch of data out of this. Which student helped which other student on which topic? We have this giant matrix, and then we can start predicting future performance. And it turns out to be very predictive, like how many students are helping other students, or if a student is helping a lot of other students, may perform well. If a student is not helping other students, may not perform well in future exams. So then we can focus on them and try helping them. So finally, I know I'm almost out of time. I'm just going to very quickly wrap up. So we do a whole bunch of other things. Just to give you an example of the stuff that these kids have been able to do, I'm incredibly proud of them. So again, keep in mind, first year, second semester, so like 6 months out of high school, they're able to use the knowledge in this linear algebra course to do things like write quantum algorithms, do game theoretic algorithms, face recognition. These are just some of the examples, but they're doing group-based projects that are at the level of final year thesis projects, or even first year postgraduate, in some cases first year postgraduate students. They spend way too much time on it, in all honesty. I'm like, hey, you guys have exceeded my expectations, and they still keep pushing themselves. Because along the way, there are community norms that are built up, there are expectations that sort of, like Chris said, friendly competition, but they really do help each other, and I'm really quite proud of them. There's a game that they create, they create questions for each other, they challenge each other with these questions, and that's useful for whatever things. I really know I'm out of time. Okay, I'll just finish. There's a forum, I'm not going to go there, it's also useful. Last 3 slides, I promise. So the way forward, this is a figure that we are quite proud of here at CUHK. So normally, in a normal class, we tend to think of teaching and learning as being basically, there's a content, fundamental concepts, so slides, and that's it, and assessment, exams, right? Those are the two boxes as educators we tend to focus on. But really, like once you start taking into account, so over here, feedback of evaluation, like those slips that we hand out, for example, or the course evaluation slips and so on. Once you make that central, once you listen to what other students are telling you, like all the stuff that I've put in over here, and I suspect possibly the same for Chris as well, it's not built in 1 year. It's not that I just decided to wake up one morning and create a class with all these different moving parts to it. It's like you listen to students, you're like, oh, that doesn't quite work. Okay, let's try this one other thing, then next year one other thing yet again, and so on. So you layer on top of it all. And then you try to take into account what the student learning needs are, build learning activities for those, try to keep reflecting on it, and it ends up just being better than that. Another way to view all of this is, so we tend to focus on, and this is due to Professor Chai, who's also part of this collaboration over here at CUHK, but we tend to focus on the content knowledge over here, like, how do you solve things? But really, there's also pedagogical knowledge, which is how do you effectively communicate those things to other people, right? And technological knowledge. Okay, now that we have these nice funky apps or online learning tools and so on, how can that help the pedagogy? How can that supercharge the pedagogy? And the TPACK framework is one way of thinking about how do you merge everything into one cohesive, gigantic whole, which is somehow just much better than anything by itself, right? So this is a very nice framework. So last slide, why do we do all of this? So unasked for, a student at the end of last year just sent me this email, anonymized for whatever. But basically, she starts off by saying, oh, I hated this course to begin with. Quite honestly, it's an intense course, lots of materials, high expectations. So even though she's really quite strong and so on, I really didn't enjoy it. But she evolved as a function of time. So she feels like she almost dropped this course, but last semester, this semester, she went to the library every day. She changed her habits. She was excited when facing challenges and learned how to manage her time. So things like this are really what we, why we educate. This is what makes us wake up in the morning and want to come out of bed, right? All right, that's it. Thank you.
So much. So we have to move right along. We'll save some time at the end for questions. Our third talk today is by Professor Darwin Lau. Darwin received his bachelor's degree in engineering, mechatronics, as well as in computer science from the University of Melbourne, Australia in 2008, and the PhD degree in robotics, also from University of Melbourne in 2014, on the modeling and analysis of anthropomorphic musculoskeletal cable-driven robots. From 2014 to 2015, he was a postdoctoral research fellow at ISIR, Université Pierre et Marie Curie, Paris, France, on the Romeo 2 project, working on predictive control walking algorithms. Presently, he is an assistant professor at the Department of Mechanical and Automation Engineering at Chinese University. His research interests include the study of kinematics, dynamics, and control of complex robotic mechanisms, such as redundantly actuated and cable-driven manipulators. The applications of the work focus on bio-inspired robots, biomechatronics, and robotic architecture and construction. So please welcome Darwin.
Yeah. So firstly, thank you for Professor Meng for the introduction and just a quick setup of the robot arms. So basically we're presenting our work on teaching using robot arms, but in a hands-on way. So I guess most of the presentation really echoes the previous two speakers, and unfortunately without a coin on my head, I'll have to rely on the robot arms in front, and that is what we put in front of class, in front of the students, and that attracts their attention in some ways. Okay, so essentially, as a bit of background, traditionally these are the way we learn a lot of these lectures in engineering, mathematics stuff, robotics. So you have a whiteboard, blackboard, and the lecturer writes on it, using starting from blackboards to whiteboards, and now we have very modern PPTs. But still, it's the same. It's still a very bidirectional. Unfortunately, I have to give a seminar like this and not as I would giving a lecture, but it's like this, right? It's a one-dimensional thing. And I guess the summaries is a bit bland and dry. And I did that the first year I taught. So when I taught in 2016-17, that was the way I taught my lectures. So then we changed, because I got bored myself presenting the topic. So it wasn't just the students that I predicted was bored, I was bored too. And then we made a robot arm that we put in front of the students, and every 4 or 5 students would have one of these in front of them. So, and this was every lecture, this was not a lab class. And then essentially the students, if the videos would even... Not sure why the videos don't play, but essentially they talk and play with the robot arms in front of them very extensively. And then essentially it's sort of like a design-based teaching, a term I learned from our colleagues from education, which I didn't know before. We observed the problems and we addressed them. So the problems that were observed, mathematical concepts like that were taught in robotics were quite abstract. So we're not teaching the hands-on programming and building robots. We were teaching the mathematics behind it. So it was very mathematical. Slides could only show things in 2D, and until we introduced more VR, AR, and 3D slides, we're still in 2D. And all the robots are in 3D. So how do we address that? Difficult to keep the attention of the students. I mean, when it was a lecture, that was basically the picture that we typically see. And of course, robotics is very physical, which is not what slides convey. So, of course, one way is we can add exercises and stuff, but another way we went about it is to add a real robot for a real robot class. So essentially, this was the classroom setting that we envisioned when we sort of designed the concept, where there'll be lots of tables, students, that may not look like that, but students would be playing with the robots and helping each other, talking to me and other TAs, and this was the real situation that was executed in the class the year after. So at least I believe we sort of got that concept through. And it all started with a very simple idea. Learn robotics with a robot arm in front of you. And of course, there are many robotic arms that are on the market, but that's not the focus. That's not the real focus of what we're doing. The problem was they were focused on making, building. That's fine, but that's not what our focus is. Our focus is teaching theory. So we need to be able to learn the theory, not just build the robot. So we build the robot for them then, and we code the robot for them. So there's no programming, no building involved. So then this is what we did, a summary. We first developed the robot arm, designing and building it, made about a set of 12, 13 robot arms for 4 or 5 students in my class of 50, third-year undergraduates. developed a tablet application that basically runs on Android, and that aligns exactly with the lecture content. So it wasn't just about giving them a robot arm, it was making sure that the content matched what I was teaching. And the only way to do it was to either me teach what was out there or I make the app to match me. And then we integrate the robot and the course together. So the lecture slides, exercises, how to glue all of this during the class setting. Then we executed it and tried and learnt from all of the complexities involved. So then just the first stage, so this was sort of like a 1-year project that started in sort of last year, and we just wanted to make a robot arm that wasn't a toy. Well, it was a toy in the end, but it doesn't look as much like a toy. So these were the products of the robot arms that we designed ourselves, and then we made a set of them for the class. So we got support from the university to do so. We designed the robot arms. That was the way to fit within that budget, basically. So then we had to 3D print it ourselves because that was, again, the way to fit inside the budget. And then we assembled it, on campus. And then stage 2 was developing the app, which was actually probably the first part was straightforward. This was probably the more interesting and challenging and never-ending part of this whole experience, and it's still not ended. So we chose to use tablets. We designed a tablet Android application that covered 4 main parts of the course, and essentially, so far we've built a total of 23 different pages covering different subtopics within the course. So, and then basically I could say we use these in every one of the lectures through the whole course. So 13 weeks of 2 lectures a week, the robot arm was there and we had exercises every time. And then the course integration. So we had the app content, but we need to integrate the lectures and everything to make it explainable and understandable. So the lecture slides explain, for example, filtering. Then we'd have a real sensor on the robot arm running the filter, and you could change parameters, and then you could see the results and hopefully link the theoretical content with the real content or the real situation, and what could go wrong. Things that were complicated, like, frames that, you can imagine the picture above trying to draw in 3D on a 2D slide would not make sense. So then we would stick toothpicks frames onto the robot arm, and then they would see the frames move in 3D. So that's a way of overcoming the limitations of 2D slides. Complex mathematics, plot the graphs that they dynamically put in the equations in there, press play, the robot arm moves, and then you observe what happens. Does the robot arm jerk at the end, or does it smooth when it's moving? How do the equations affect all that? And these are all, you see it in front of you. I mean, I try to explain it, they might go nod their heads, but afterwards they may not remember it. If they see it and they see the behavior is not good, they might remember it better. That's at least the anticipation. So the execution turned out to be very difficult, but we had an extremely interactive class. So we have 2 of these such classrooms at CUHK. I booked one of them, and they were so popular that I ended up with an 8:30 morning class, which the students absolutely loved, including myself. and that was the situation that we had there. And then there were different modes of teaching during this. Firstly, we had lectures where, within the class, they had these slides. I was getting dizzy. I was turning 360 around all the tables because I was standing in the middle, trying to make sure I get eye contact with the tables. And then I was teaching the theory. I was teaching just like I would normally the theory. But of course, that environment also made it more interactive. So people were happy to probably ask a little more questions, though, we still did work on that. Solving mathematical exercises. There were these fantastic whiteboards right behind them. And then we said exercise time. And then they start doing groups of the tables and do these exercises. And we had myself and 3 other teaching assistants that were in the classroom. I removed tutorial classes altogether and put all the resources into the lectures because there were only like 3 students that would go to tutorials on a regular basis. So then I just removed it. And then we got enough manpower to help do this. Hands-on exercises, playing with the robot arm. The exercises link the mathematics to the theory, to the robot arm, with the apps that get to, press and play it, and that's essentially the way it operated. And then these were, we needed more manpower in each of the lectures, which was, the unfortunate thing, but also better for the students in that sense. It sort of made better our teacher-to-student ratio from this matter. So instead of 1 to 50, now it became 4 to 50. Okay, and then we executed this in 2 stages. We tried a summer institute, and these were some of the pictures of them playing with. We put a light on the end of the robot arm, and they were drawing with it and just for fun. But we also did it for the 3rd year robotics class, and next year I intend to continue this, and we'll see how we can improve on this. So essentially a few quick demonstrations. I'm not sure why the videos don't load. Ooh, it's been on my laptop, so it's a bit, yeah, it's on my laptop, so it's weird that it doesn't. Okay. Okay, so unfortunately, I think, I don't know why, it's a technical glitch. So basically, I'll explain the concept. Basically, you see sensor data, which is, the signals that the robot, where the robot arm is, right? And as you move the robot arm, then you're going to see, and at the end, we can have a hands-on demo where people are interested come down and have a look physically at the app running, and you see the filtering signal, and you could change the window of the filter, and then you could, in real time, see the changes on the tablet app as you're moving the robot arm. So that's a way of interacting rather than just being told or shown a video, which, of course, as we know, videos may not work either. Okay, another one is something like singularity. So we learned this concept in mathematics. It's called matrix Jacobians, and there's a determinant, and there's a singularity. What does that mean? Well, so what we did was you move the robot arm. As you get closer to the singular configuration, you saw that the matrix was losing some of the numbers that were getting very small. And then it started to tell them, this is what happens when you're getting towards singularity. When your arm is straight, you see these very small numbers compared to other positions. So they move the robot arm and get to see it. Another example, which hopefully we could demonstrate then later, is doing trajectories where they have to plan a path. Robot moves from point A to point B. How do you plan the motion? By inputting equations into there. Rather than inputting the 2 points, you input the equations. So they have to first calculate the equations on the board, calculate all the coefficients, enter it into it, and press play and see if it runs, and see if it runs properly. And this is a way for them to, again, exercise and understand what is happening. So essentially, these are the features and the teaching experience. Essentially, we want active and inquiry-based learning, so it's helping to increase the attention and satisfaction during the course. We want these groups to let them do peer learning. They teach each other, help each other, since we're too busy to deal with all of them, and hopefully it increases the students' confidence behind it as they're doing this. Real examples, so, to say that university theory is not fake, which many students tend to believe, and it gives relevance to this content to the real world, because they're playing with the real robot arm, and then they're doing some real exercises. Let them have some fun, and hopefully excite them to keep them awake, increasing their attention to the class. I mean, that has certainly, there were much less students sleeping during these classes. Probably because they couldn't sleep more than anything else, because they were in close attention all the time, and so they couldn't sleep, even at 8:30 in the morning. Visualization of concepts, so increasing their confidence and satisfaction, hopefully, to the course. And this was the classroom situation. So I just want to summarize the situation. There's student-teacher interaction. So when the TAs and myself walk around, there is interaction. There's student-student interaction, because they're helping each other. Someone's writing, someone's talking, someone's telling them you're writing the wrong thing, and they keep yelling at each other, but that's healthy, right, in some ways. Student and the robot arm. Students, well, they don't talk to the robot arm, but at least what they press and play, the robot arm moves and gives them some response, and hopefully also teaches them. So these sort of relationships, I guess, is sort of enriching the typical just one-to-one, or one-to-many, sorry. Balance is difficult, how to balance between all these exercises. So next I'm going to go through a lot of issues that we've had to go through. So balancing, with such a new technique, there's new styles of teaching, and extremely complicated for me to get my head around how to distribute the lecture times between exercises, theory. I've removed tutorials, so now each week I've only got 3 hours to go through exercises, tutorials, hands-on. I still have labs, but that's a different thing. Too little hands-on time, and then students may go to sleep again. So we need to make sure we keep them awake. And how to transition between these modes, and I'm still learning and struggling. So interesting observations. Some topics were taught slower, but some were quicker. So it depends on the topic, and hopefully next year I could get a better grasp on getting much more effective use of this. Another one, student variation. So students within a group were fine, but students between groups, because some group work faster, some group work slower. How do you get them to help the struggling students and help each other? So that's a challenge. Changes for next year, we hope that we have more exercises, so challenge the smart ones to go beyond that, or the ones that were quick anyway. Extra reading, so the ones that are struggling could actually have some reference rather than relying on verbal, very ancient technique. have it documented. And then promote groups to finish earlier to go maybe go out and help the other groups so I could at least get on with my lectures. And basically this is sort of what we've been doing, trying to do for the next version is we want instructions that you just press a button and pop-up comes up and you get instructions, self-learning component of, so adding another one, app and person self-learning. Exercise instructions, so that when you press on these exercises, they'll pop up the exercise instructions and they'll save me trying to explain it in a very verbose way, whereas there'll be a step-by-step, step 1, do this, step 2, do that, what is the answer, and then wave and tell your teacher to come and explain to them, for example. Some theoretical information, so we could embed a lot of this theoretical fundamental mathematics in content, like lecture slides, a bit like these keywords that they could click and go into. These are the keyword that jumps back into the lecture content to remind them what they have learned. Teaching practice, so this was a big change. We have to adapt to a new teaching style. It's like a lecture, tutorial, and laboratory mixed into one, which was quite overwhelming for myself, to say the least. But it was an interesting experience. We all learned a bit, I think, a lot, and we discussed, had meetings every week because we were confused at phenomena we were looking at. I think the TAs out there could relate to that very much. And I'll be honest, it was a lot of work. It was really a lot of work in half a year to do this, which was fun, but a lot of work. Developing the application really took a lot of thinking, and setting up at each class was time-consuming, and that's one problem. If the robots could just walk into class themselves, land themselves on the table, and start operating, that'd be great. But these days, no. These days, this is what happens before and after each class. I've got a bunch of TAs and trying to set up the robot arms for them and within minimal time so it doesn't distract the learning experience. And the challenges to overcome. But some benefits, of course, not everything's bad. We get some immediate feedback. Rather than lectures where I ask, do you understand? Hands up if you do. And then basically, this would be the situation, right? No hands will go up. But of course, that's not the point, I'm trying to say. But within this, I see them. They look at the robot arm, bedazzled. When you say, do exercise, and they look at the robot arm, and they're like, they're confused. And we could tell. So we immediately go over and spend some time talking to the confused ones. The ones that are working are fine, and we leave them. So it's the confused ones that are really a problem. So we see them, and we know which group, which tables are typically the ones we need to give more help, either from the fundamental mathematics or just explaining things. So very immediate feedback. And if the whole class is confused, we immediately stop them and help. But usually it's more individual groups getting confused. And the students become more self-aware. So for that year, we had to have weekly meetings and reflections just to get everything on pace. Helps us, active learning really helps to understand better because they understand what they don't know much better, getting to touch the robot arm, explore different variables and its effects with the physical thing. I mean, I can't just testify whether they still remember the concepts from last year, but at least I have good faith to believe that at least it's a little more memorable than otherwise, but, and also makes them think more about the topic and what it means. Telling them, it's different. Telling them in a static way is different to experiencing in real thing. And that's one thing I certainly felt from the students' immediate feedback. Increasing their attention. So basically, I didn't do the actual numbers. I really regretted not actually counting the entry into the class, but really they did. And I think it was more than my attendance last year, and I had a really awkward time in the morning for them to come. So at least it shows they were interested and they felt it may give some value. A new experiment, so we did some surveys, we had collaboration and help from CLEAR and also Faculty of Education. Opinions of the classroom were quite positive. We did some surveys on different categories: attention, relevance, confidence, satisfaction. There were nothing actually. We were hoping to get more interesting data to publish, but we couldn't get that. There were no particularly high or low categories that could compare. They were all just averaged quite well. The students seemed to be happy. And then, we were hoping to get more stuff that we could write long, lengthy essays about, but we couldn't. So to supplement the actual lectures, we had open-ended creative projects. This is to basically say, I give them a robot arm, not this one, a different one, and they had to design their own tools on it, use the theory of the robot arm to do some task. Every group, we had 10 groups, we had like 15 groups, 3 students each. Each group had to do something different. They submitted an early proposal, so we could vet it. They did the work, they submitted a report, and then did a video, I have good faith to believe that it's not playing, but I could open up the video in a separate window. And essentially they had to do a video. So it was one way to present, for them to present and get a different experience in doing the group work. And they were creatively looking at all sorts of different tasks. And they were quite creative. So they had a lot of fun, which was, I think, the important part. Sorry for all of the hierarchical folders. So they made a video. They even put music to it. Much beyond what I expected. I told them don't spend much time.
I saw a very great robot arm here. So what is it about?
So basically, you can see this is a water window cleaning robot arm. So its task is mainly from window cleaning. So as we can see from the news that many domestic workers accidentally fell from their homes while they are cleaning windows. So we are going to make a robot arm to replace some of them.
And of course that robot arm is not going to actually successfully replacing these domestic workers.
So can you introduce us more about
it's a thought.
The robot?
So they actually made the part that was in green and orange, they made themselves out of 3D printing. That wasn't in the scope, that was in creativity. And then they had to do a demonstration. This was using the kinematics, the mathematics they had to learn in the course in order to be able to do it. Sprayed some water and tried to, actually do the motion, It was a bit of fun. It was a bit of fun. Made sure it had to be very relevant to the course content. And I let their creativity go. Some probably spent much too much time than I wanted them to. But, it is what it is. So that was a good supplement to the hands-on nature of the course, actually, I felt. But it wasn't anything, special. It was quite normal in terms of the nature. In conclusion, it was an interesting experiment and experience. The second year hopefully should be less work. I say that. Obviously, typically it'll be more work. And I intend to fine-tune and polish this. It was a fun experience. Learned a lot from observing students' behavior because I would not regard myself an educator. I regard myself just a teacher. But it has been helping me to educate me to look at how teaching may work in some ways. A new teaching method, I believe, so it's not just about robotics. It could be used in a lot of different mathematics, electronics, a lot of different areas. Students need to adapt to it, but we found they adapted quite quickly, quite different to the traditional experience, and hopefully we could go beyond that and look at it, maybe even towards junior students, first year or high school, because this hands-on approach gives this attractiveness. So we hope that we could do more work, and then hopefully if there's any foster discussion between different parties, acknowledgements to a team of TAs and yes. Team of TAs and also my main developer, Samuel, who really spent a lot of effort developing this. And I asked them to write a comment. They went overboard except for the first one. And fun is good. So I think that's an important part of engineering and robotics. So that's it for my slides. If we have a little bit of time, I was asking maybe Samuel could do a quick demo with it, and then after the quick demo, since it's the last talk, if anyone's interested, feel free to come down and play with the app in the robot arm, just so we could chat more. So that's it for my part. I'll pass the ball over to Samuel.
Yep. So to get an idea of how the robot arm works, first you have everything connected, and then you open up from the list of modules. You open up the whatever modules that we're currently teaching, and then first I will make it run. Let's say if I want to make the robot arm move to a particular point at a particular time, we first I'll make a very simple modules to show that what it can be done, and let's say if I wanted to move from point to point, and first we have them just enter a point or two and have it work, and the app will show that these like if you use the cubic equations, this will be how the equation looks like. So it's like an example. And then there will also be graphs to let you know that the acceleration or the position will look something like this. So this is more like a demo to show them why on earth we are learning this in the lecture, because it helps you move the robot arm. And then in the following apps pages, it will be the students' turn to derive those equations and find those values and control it themselves. And so this is a little taste of what it looks like. And maybe afterwards, if you have time and you're interested, you can come and have a closer look. Thank you.
Thank you very much. So thank you, Don, for even bringing your lab, part of your lab, to this lecture theater. We have just a short period of time for any questions that you may have regarding all the three talks. Any questions from the audience? I guess we've kept everybody here. Oh, yeah, one question, Jimmy, please.
I have a question for Chris. First of all, thank you very much for the very interesting experience sharing for flipped classroom. I'm from here. You were talking about educating a class of 300 students using this flipped classroom approach. I'm just wondering what the resource implication would be. Like how many sessions do you have to run? Like arranging all these tables, students sitting at the corner, and I don't think you can do it with 300 students, right?
No, so we could do about 50 students in a session.
Okay.
So then we would run as many sessions as we needed. In the experimental thing, we were aiming at 50. We ended up with like 65 or 70. It was sort of everybody hung from the wall. But to teach the flip section for the entire 300 students, we would have to run multiple sessions. But the way we do our course now is the recitation sections we run, we actually have 12 different sections. So this would fit right into the sort of our standard way of partitioning up the students into smaller groups and working with them. So they would do 3 hours a week worth of the flip section, 2 1.5-hour sections. And that actually, they did as much learning there as they did in our standard 4 contact hour with 2 lectures and 2 recitations. So it's actually, because of the way we run our staff, if each staff member handled one of the sections, we would be in good shape, plus some LAs and TAs.
So you require to have all the TAs in the classroom at the same time?
Not all. I think we would get away with 1 or 2 TAs and 3 or 4 LAs in each section. So each staff member would end up doing, say, 2 sections, and that would be a sort of a very standard teaching load. So in terms of the teaching hours we would require of the staff, it wouldn't be greater. It would just be reorganized.
Do you think a different classroom setting is important? Like, we cannot do it in such a lecture hall, right? So the university would have to build different classrooms for your purpose, right?
Yes, I mean, the room that we designed there has been used for many different classes, but basically a large room with square tables seems to be, there's a whole bunch of different teaching techniques where that seems to work really well. Obviously, as Sid pointed, this would be a disaster at a room like this because you're supposed to work together and you really need to, physically it would be hard to put our heads together. But it's not a demanding physical setup, right? It's really, any large rectangular classroom could be made to serve, just change the rows to groups. I don't think it would be a hard experiment to run for people to try.
Thank you.
Yep.
Thank you. Any other questions? Well, actually, in fact, Chris and Victor are here with us for 2.5 days. We have a lot of research meetings and discussions. So we have just one part, which is this afternoon on the public lectures. And it's wonderful to be able to hear from Chris and also our colleagues on their amazing work. in the interest of time, I guess we can have more interactive discussions later on, but I probably need to bring this Q&A part to a close.
Okay. Thank you, Professor Meng. To express our appreciation, we have prepared some souvenirs for Professor Chris TERMAN and Professor Victor Zhu. May I invite Professor Meng to present the souvenirs for us? Professor Meng, please. Professor Zhu, please. Thank you very much. This will be the end of the CUHK-MIT Joint Workshop on e-learning. We hope you have enjoyed the workshop. Thank you once again for coming.
So what sort of commands are you sending over? Are you sending sort of low-level stepping motor commands, or are you actually, does the electronics know about position and you're just saying go here?
Yeah, all the processes are mainly done on the tablet, and so we're only sending commands.